heard over the past 8 weeks, 9 weeks, has been sort of an outline of lunar science, sort of what we want to know about the moon, why it's important, some of the kinds of data we're going to be getting to look at that. And then last time, Dean gave us a very nice review of Apollo and the Apollo experience, what we found out, what works on the moon, what doesn't work on the moon so well, how we can enhance our exploration experience on the moon. And I want to look ahead today. This is going to be a little bit of a combination. You're going to hear some things you've already heard, but you're going to hear some new stuff too. And I want to delve a little more philosophically in why we're going to the moon, what we want to accomplish, and how we're going to accomplish it. Next slide. I include this slide in my stump speech, what I call my stump speech about why we're going back to the moon. And this is one of the main reasons I think we're going back to the moon, and that is to become a spacefaring species. What we need to do on the moon is to learn those skills that we need to accomplish that. And that includes learning how to survive and thrive on another world, how to live on another world, how to extract what you need from what's there. But one of the key things is a school for exploration, understanding how to explore. Now, that involves not only the techniques of exploration, but also the very specific activities that you use to get the key information you need to answer the science questions that we've been posing for pretty much all summer. And in addition, since the moon is a key stepping stone to where we're going to Mars and to other planets, learning how to do these things on the moon makes perfect sense, because the moon is a little planet that's had a very complex evolution, and we can understand how to do things like field geology, geological exploration, how to set up stations and maintain them on the moon, so that when we go elsewhere, we know those techniques, we know where the pitfalls are, and we know how to avoid the serious mistakes. Next slide. So I want to break this talk down into these activities. What are we going to do on the moon? When we get to the moon, what are we going to do there? We're going to explore, we're going to emplace things, and we're going to maintain them. And fundamentally, we've got a whole planet to explore. We've got a bunch of different processes that we've described: volcanism, impact, tectonism, regolith formation, and space weathering. How do they work in detail? What kinds of information do you need to address that? And by learning how to do that on the moon, we're preparing to go elsewhere, because the kinds of things we're doing on the moon are the same kinds of things we'll do on the planets. But in addition, we want to set up packages and experiments that are going to be long-term observational stations and observatories. The moon is a very nice platform for a lot of different kinds of observations. We sort of did this on Apollo. Remember about the ALSEPs. We set out experiment packages. That was an enormously successful activity, because that network, the ALSEP network emplaced by the Apollo astronauts, lasted for 7 years. The only reason it stopped working is because we turned it off. It would have continued to work for at least another several years if we had ponied up the money to collect the data and analyze it. And occasionally, things are going to break. Things don't continue to work forever. We need to be able to maintain those when that happens. And understanding how to do that is another thing that we need to accomplish when we go back to the moon. Next slide. Don't we know how to do this already? Am I dwelling on the obvious here? My contention is that no, we don't. That Apollo, in toto, the entire Apollo experience, wasn't long enough and wasn't complicated enough and detailed enough to give us this kind of information. Yes, we scratched the surface. Yes, we got a feel for sort of the difference between initial reconnaissance and detailed field study. And we set up stations that ended up lasting a long time. But the longest stay time on the moon was three days. And we're going to exceed that in our first visit back. So fundamentally, we're talking about a different scale of activity, a different level, and a different quantity of exploration on the new program than what we did with Apollo. The other thing is that occasionally things broke on Apollo, like the fenders on the LRVs, and we improvised a fix. But if things break in the future and we're on the moon and we're going to continue to use this equipment, we can't jury-rig everything. We need to be able to fix things, maintain them, and do that on a repeated basis. Next slide. Okay, now I want to step back. I've pulled out another couple slides because I think we need to step back and really consider what we're really trying to do when we explore. What is exploration? Why do we do it at all? Why do we care about this? Well, my contention has always been that fundamentally humans are hardwired with the urge to explore, and I think it grew out of an evolutionary trait that we have. And that is, by exploring, you broaden your imagination and your knowledge base, and that gives you a survival edge over those that don't explore. Basically, when you go to new places, you see new things, you're forced to devise new explanations, you have a broader and more flexible imagination, so that when you come against other problems, you're able to apply creative solutions much more easily. In other words, the imagination is like a muscle. The more you exercise it, the more supple and more stronger it becomes. And I also think, so basically exploration improves our ability to solve problems. When you explore, you see new things, you devise new solutions. That way, when you approach a different problem, you're able to actually imagine more solutions than you would have otherwise, and to pose the right questions, or at least to pose a question that can be answered. And finally, I think exploration in a collective sense inspires the best in society. It inspires the creative, innovative people, because people that are drawn to this field are the intelligent, creative people that tend to imagine new kinds of things. Next slide, please. Exploration and science aren't the same. Exploration is about going over the next hill, seeing what's there, looking at new and alien terrains. It's not really directed. It has a structure, but it's not directed. But science is a very structured activity. It is the process by which we explain nature. And exploration and science aren't totally equivalent. They're both dynamic, not static, but science always follows the exploration, so exploration enables science. Next slide. I contend that exploration is broader and richer than science because it includes two aspects that science doesn't. In addition to the imaginative exploration and intellectual exploration that enables science, you also have basically infrastructure development and wealth creation. Those are certainly parts of exploration historically, and the Spanish conquistadors didn't come to the Americas for science. And traditionally, the idea of pure scientific exploration is a fairly recent modern concept, 19th and 20th century. However, once you're there, once you're in a new terrain where you have an exploratory infrastructure developed, you are enabling science because you have access to a new exotic environment, and you have the logistical capability to do much more creative, much more capable kinds of experiments and observations. Next slide. Why people? Why can't you do all this with robots? The perennial debate. My contention is that fundamentally people bring cognitive abilities to exploration that machines cannot yet attain, and in fact, in my opinion, won't be able to obtain for some time. Fundamentally, the human mind interacting with an alien environment has not been topped. It has not been topped by any robot or machine yet built or even conceived. Now, that doesn't mean there's not a place for robots in exploration. Robots gather preliminary data. They can reconnoiter sites for more detailed exploration later, but fundamentally robots are only designed to collect the information that we design and build into them. They typically cannot adapt to new situations, whereas people can. Next slide. I also think there's an emotional dimension to this. I think that people inspire, and the drama of human exploration captivates the public. It always has. And especially true when things don't go exactly according to plan. So there's the intellectual basis for human exploration, which I contend largely revolves around the ability of people to think, and then there's the emotional appeal, which is the inspiration and dramatic appeal. Next slide. All right, let's review one more time. You've seen this slide before, but I just wanted to review it. We're dealing with a rocky planet, has a crust mantle and core, heavily cratered surface. Parts of the surface have been resurfaced by volcanic lavas, and fundamentally what we're interested in is the uppermost few meters to tens of meters of the moon, because that's what we can access. Now, there are ways to get down below that layer by using the natural processes of the moon. For example, craters dig down, in some cases, many kilometers. So when you look at that material, you're not looking at the moon as it is right at the surface, but you can infer the properties of the moon at depth. But what we're trying to understand is this body in its totality, its processes, its environment, and its history. Next slide. So what are the kinds of things we want to address when we go back to the moon, when we explore? Well, how do we best explore a planet? What's the optimum mix of people and machines? If you allow that I'm correct, for the sake of argument, that you need robots and people, well, what comes first, what does what, and what's the optimum mix? How many robotic missions do you fly versus what you send people to do? How do you plan these traverses and to basically optimize your time? No matter how much time you have on the moon, ultimately you need to have some kind of a field plan. Otherwise, you might spend a lot of time aimlessly going and doing stuff that's not necessarily relevant to solving problems. What are the best jobs for people? What are the best jobs for machines? I almost included a figure here I didn't include. It's one of my favorite drawings. This is back from the old lunar base days in the 1980s. And it was a drawing that was everything wrong about the role of people in space. It had a picture of an ISRU experiment, and the astronaut was shoveling dirt in with a spade. Now, to my mind, that is using a person as a robot, and that's not what we want to do. We want to be able to allow people to be creative and use their time to actually make significant discoveries. So what are those requirements? What is the requirement of geological field work, and how is it done in practice? Next slide. Okay, I want to, we sort of touched on this, and Dean talked a lot about it last week in terms of both the training for the astronauts and what they actually did on the moon. I contend there's a fundamental twofold division of geological field work into reconnaissance and what I call field study. In reconnaissance, basically, you're going to a site, you're walking it to the extent that you can, you're trying to inventory what processes have occurred, what the diversity of rock types are. You're just trying to get a feel for how the site is put together geologically. Remember, in geology, we're interested in not 3 dimensions, but 4 dimensions. We're interested in the lateral heterogeneity, the vertical dimension, which is what we look for when we look at layered outcrops. But that vertical dimension actually implies a 4th dimension, and that's time. So we're looking both at spatial and temporal variations in process, in unit, and in compositions. And those are the kinds of things you study when you go out into the field. When you do field study, basically field study is like reconnaissance, only in much greater detail. So we're trying to fill in the missing gaps. Once you've gone out to a site, you sort of know what's there, you know where it occurs. When you actually study the outcrops in detail, that's when you fill in the blank spots of the map. You're basically trying to understand as best you can, in the most comprehensive manner you can, what's happened in a given area and what the history of that area is. Now, typically, you collect samples. You collect pieces of outcrop or pieces of float, return them to the Earth, and you do laboratory analysis of it. The lab analysis informs you about certain things. It can inform you about the detailed compositions you find. It can tell you about the ages of those things. If there's some question as to what unit predated another unit, if you can date the 2 rocks in the laboratory, you can get sometimes a distinguishing. You'll know which is older and which is younger. And that in turn informs your work when you go back into the field. Because the key thing about geology is you don't just go to one site and check it off and then never go back and look at it again. You typically visit some sites repeatedly. And in fact, there's field sites on the Earth that have been studied for 200 years, and people still go to them. And why do they do that? Because they're still learning things from them. So in other words, understanding the natural condition of a planet, the natural state, how it's put together temporally and spatially, involves going into the field. The field is the planet itself, and studying the processes and materials that are on display there. That's what field geology is. Next slide. Now, it's a matter of degree. There's no solid line that divides reconnaissance from field study. Effectively, all the Apollo missions did geological reconnaissance. Some of the latter ones actually did real field study, where they were able to spend a certain amount of time in detail. And what I'm thinking of particularly in the Apollo experience were the visits to North Ray Crater on Apollo 16 and the visits to the Tomb of Cephas on Apollo 17. In both of those cases, they were detailed study of what passed for outcrop there. And the importance there I want to get to is bedrock is important. Bedrock is important because that's the actual units that the upper crust of the planet is put together with. When we land on the moon and we stand on the moon, we're standing on regolith, which is this debris blanket that's generated on top of the bedrock. To really understand how the moon is put together in regional units, we need to look at bedrock and sampled bedrock, because that's actually what the upper crust of the moon is made of. Now, on Earth, bedrock is fairly easy to find, especially in the western states, where you have a lot of very nice outcrops you can study. Here's someplace in the western United States, big solid rock outcrops. If you're back east somewhere where there's a lot of vegetation and a lot of tree cover, it's very hard to find these. And typically what you do is you wander the field area, identifying as many outcrops as you can. Then you sit down with a topographic map with the notes of those outcrops and then try to tie all the lines together. It's sort of like those pictures where you connect the dots, where you're trying to imagine what the picture is that's emerging by little pieces of information here and there. Next slide. Now, field and lab analysis go hand in hand, and they're not entirely separate. They were in Apollo because for each Apollo site, we knew we were never going back to that site on Apollo. So we had to get, as best we could, the diversity and a comprehensive suite of rocks that represented the sites we went to, because we weren't going back. And so in that case, you did the field work and then lab work followed. But in actual fact, it's an iterative process. On Earth, you collect samples, you analyze them, you go back to the outcrop to collect additional samples. You may find, for example, in some layered intrusions, this is where you have a magma body where the rock is separated into different units based on differentiation due to gravity settling. In some cases you can see that with the eye. You can actually see different rock units. In some cases you can't. There's actually a layered intrusion in Greenland called the Skirgard, where you actually have what they call cryptic layering. You can't really see it except through sample analysis. And to see that, you have to very carefully sample the outcrops at intervals, do the analysis in the lab, and then relate that to what you've sampled in the field. So this process of going and looking at rocks, doing sample analysis, and then going back actually is very important. A key question, and this is something we have not yet answered, is how much of this analysis do we actually want to do on the moon? In other words, if you've got, for example, a sortie mission where you go and you spend 4 days and you go out to a bunch of different sites and you collect some samples, do you want to do any analysis on the moon before you come back? Because if you do, you might actually go back to that outcrop before you leave and actually resample it and do a much better job. In addition, for certain types of rocks, for example, basalt lavas, you don't need multiple kilograms. You don't need the Great Scott, the 15555, which is a huge boulder basalt, because it's all the same stuff. It's a fine grained, a very small sample of that goes a long way. But for a complex rock like a breccia, which is made up of multiple different components, the bigger the better, because the bigger it is, the more class and the more things you have to look at. So understanding this is actually an important task. There is bedrock on the moon. We've seen it throughout the summer lectures here. We find it in crater walls. We find it in the walls of rills and graben. It can be sampled. In addition, there's a stuff I'm calling pseudo-bedrock, and that's like, those are the boulders that you find at the foot of massifs, which clearly have some source somewhere up on the mountain. Typically you can correlate it, either visually or with remote sensing data. And in this case, you're actually sampling bedrock, but not directly, because you can't get to the top of the mountain, yet here's a boulder that actually has a trail up the mountain. You can trace it to a ledge or an outcrop. You've actually sampled that outcrop. Now, admittedly, that inference is not as secure as if you were standing on a real outcrop, but it's a good substitute when you have inaccessible targets. Next slide. Okay, mapping is a key thing to geologists. It's not something that we do just so we can find our way around. For a geoscientist, a map is a representation of the planet's surface, but it's also a place where we plot key information. And how that information plots on a map and relates to each other tells us fundamentally how the planet is put together. Here's a geologic map over here of the area near the crater Copernicus. It's the image on the bottom. And what you see, there are different colored units. Those colors are not there to make the map pretty, although it does do that. They're actually there to convey information about relative age. Things that are yellow and green on this map are actually younger than things that are blue and pink. So effectively, you've classified the surface deposits in terms of relative age before you've even gotten there. And then once you've gotten there, the map doesn't suddenly go into a vault and it's established knowledge. A map is a working tool. It is a working record of synthesis of field observations. And so over time, what we want to do is to build up maps that have increasing levels of detail and increasing levels of reliability, because that is effectively our experimental record. Maps, geologic maps, are the experimental records of field geology. Next slide. There are different kinds of ways you can cover the ground. You could go out and just wander around at random and pick up rocks. That's one way. And in fact, that's one way you might do a robotic traverse and sample return, is send a robot down, have it cover as much ground as possible, and pick up the diversity that it can observe. Typically what you do, though, is you do reconnaissance surveys, field traverses, and transects, which are interplays between field geology and field geophysics. Traverses are sort of what we did with the LRVs on the Apollo J missions. We basically tried to identify a principal target or set of targets and then plan a rover trip such that we would visit as many of these as we could, budgeting time for each station. Now, a drawback to that is if your plan is too rigid, then if you make a discovery and you decide to spend some time there, you may get hosed down the line. That happened on Apollo 17. They decided to extend the time at the South Massif by half an hour, and that left them only 30 minutes at Shorty Crater, where they made another major discovery. And so that's the dilemma of strict field planning versus giving people a long leash. My sense is that when we go back to the moon, we want to give the crew as much latitude and as long a leash as possible, because that's what really encourages the making of real discoveries. Now, transects are where you lay out instruments that not only characterize the surface, but also characterize the subsurface. And typically what I'm thinking of here are things like geophone lines that look below the surface, look for three-dimensional structure to some depth. And it's a very common technique in terrestrial science. Typically, geologists and geophysicists actually work together on this. I know it's hard to believe, but that does happen. And you do tend to get real insight into the shallow makeup of the lunar crust, of any crust, planetary crust, when you do this kind of thing. Next slide. We recently had a workshop at the beginning of the summer that Wendell sponsored at the LPI, where we had 2 teams of geologists look at 2 sortie targets and basically plan out traverses. And the object here was, given the existing data, and we used existing data, largely Apollometric and Clementine compositional data, could you plan and execute sort of a super Apollo, a super J kind of mission? And I think the results were quite interesting. The traverses that came out were really quite well done. There were limits on this. We couldn't exceed 30 kilometers in one day. Was that correct? 30 kilometers? And the idea was to cover as much diversity of material and process as you could. This landing site is on the floor of the crater Alphonsus, which is a big frontside crater. It's a floor fracture crater, and it actually has dark halo craters. And this Ravi up here in the right side is an example of a volcanic vent. And the object here was to characterize the explosive processes of volcanism that occurred in the creation of that landform. Next slide. The other target was Ziolkowski, which was a farside crater that's a large highland crater filled partly with Mare basalt. We picked a landing site between the central peak and the wall material and laid out a series of traverses that pretty much covered all the diversity that we were able to identify within that area. So these were for very limited, short duration sortie missions, and we found that it's possible with the existing data to actually draw out fairly good general field plans. It's important to emphasize in each of these we wanted to give the crews as much latitude as we could, so we planned many more stations than we actually planned on actually stopping at and doing, with the object being that as you're in the field making observations and discoveries, you could adapt the field plan to what you were finding. Next slide. But a key thing in terms of covering this diversity and doing geological exploration is mobility. And there are sort of 2 ways to get that. The Apollo LRV type rover, or the unpressurized rover, basically the astronauts are in the suit. They're out effectively for a work day. The Apollo JEVAs were 8 hours long, maybe 10 hours. All the crews say they could have survived for another couple hours. So we're talking about 10 hours or so with maybe 20 kilometers or so radius of operation. That's actually quite adequate to do a very thorough job over multiple days at these complex sites. However, if you're really going to cover the large-scale regional diversity of the moon, you need effectively a different kind of approach. And in this case, you want to go to something similar to a pressurized submersible, which is a pressurized rover that would allow you to traverse anywhere tens to hundreds of kilometers. This is a map that John Gruner prepared showing from the South Pole you could actually reach within the radius of a pressurized rover many different diverse geological targets, giving us a big picture, a very nice picture of how this part of the moon, which is part of the ancient crust of the South Pole Lake and Basin, actually formed and evolved. In this case, the astronauts don't actually go outside the rover very much. They have robotic arms that can manipulate, that you don't necessarily have to get out. We should always give them the opportunity to do that, though, because in some cases you're going to want to go up to certain outcrops and actually look at them in some detail with your own eyes. Next slide. Okay, I want to make a comment about samples. Why do we care about samples? Fundamentally, the reason we collect rocks and soils and bring them back to Earth is because you cannot bring to the moon all of the techniques and equipment that you need to study the rocks in place. They're just too massive, they're too difficult, they require sample preparation. That's why we collect samples. And I'm thinking about things here like radiometric dates. The way radiometric dates are done is you have a rock, you literally take it apart grain by grain, and you separate the minerals and then measure the isotopic ratios in each mineral, and that will define what's called an isochron, which is basically gives you the crystallization age of that rock. Now that is very painstaking, difficult, tedious work, and it can't be automated, or at least it can't be automated very well. So when you're doing these kinds of investigations, you really need the very highly sophisticated, massive, power-hungry equipment that's only available in terrestrial laboratories. So fundamentally, the other aspect of having samples is that you create a permanent reference collection. Once you've got a sample and it's curated properly, you know that I've been to that site, I actually have a sample of it. If I come up with a new technique or a new way of analyzing things, I can go back and look at that. I don't have to go back and plan a separate trip to the moon to revisit the site. I've got samples of it, so I can apply this new technique to those rocks. Finally, you have access by many different people with many different techniques to the samples. Rather than just one or two, or even the ones that we can think of. We don't claim to be all powerful. It may actually work out that some people have a different approach to studying samples. So having a sample collection allows them access to the same kinds of things you're doing. So, how do you sample the moon? And the conclusion from this slide I want you to take away is, what is the real goal of sample collection? Well, this is the same goal of all scientific exploration of space. Our goal is not data, and our goal is not rocks. Our goal is knowledge. We're exploring to understand. We're exploring to understand history and process. So samples are a means to an end. They're not an end unto themselves. Next slide. I think there are sort of two classes of sample sites on the moon, and this was developed in a paper that Graham Ryder and Jeff Taylor and I wrote, gosh, almost 20 years ago now. We tried to separate sample sites on the moon on the basis of reconnaissance site versus field sites. Now, I think that reconnaissance sites are appropriate for robotic sample returns. And to give you one example, here's a crater on the moon. This picture in the top middle basically is the crater Lichtenberg. It's a rayed crater. It's embayed by lava. Therefore, that lava has to be younger than the rayed crater. But rayed craters are the youngest features on the moon. So what does that imply about the lava flow? Lava flow is very young. Now, the youngest lavas we brought back on the moon from Apollo was from Apollo 12, and that was 3.15 billion years. This lava must be younger than that, but we don't know how much younger. We can count the craters, and you can estimate how much younger. And if you do that, the estimate of this is about 1 billion years, which is 3 times younger than the youngest lava brought back by Apollo. We don't know what the answer is, though, because we really don't know the flux, the impact crater flux, that well. So the ideal way to do this is to get a chunk of that lava flow and date it radiometrically in the lab. But you don't need to send a human mission here to do that, because fundamentally the regolith developed on this lava is going to be derived from the lava flow that occurred there. So if I land and pick up a couple of chips from that regolith that come from that lava flow, I've successfully sampled the flow, and therefore I can date that lava flow. So that's an example of something that has a clear context, very simple requirements: land, scoop up some soil, return it to the earth. That's an example of a reconnaissance site where you can answer the fundamental scientific questions by going and scooping up a rock. Now, on the other hand, this picture down at the bottom here is the picture of the Aristarchus Plateau. It's very complex. There's a very young crater, there's a sinuous rill, there's dark pyroclastics, there's Imbrium ejecta. There are at least 7 or 8 different major geologic units in this area. If I land here with a simple robot and I scoop the stuff up, what am I going to make of what I get? I'm going to get a very complex sample, a very complex regolith with a lot of different things in it. I'm not going to be sure which came from what unit, and it's going to be very hard to decipher that. Therefore, I think a site like this requires human field study. It requires humans landing and being able to traverse and associating and collecting samples with some kind of regional unit. It all comes down to the fundamental issue, is that a sample is just that, a sample of a unit. And when you have a sample from the moon, you need to be able to relate that to some kind of regional unit, of regional significance. Otherwise, it has much less value. Right? We have a lot of samples already. People are talking about Mars sample return. We have a lot of samples from Mars already. They're the Mars meteorites. Now, why aren't they satisfied with that? Because fundamentally, we don't know where they came from on Mars. We don't know what they represent. Do they represent lava flows? If so, where are they? Right? Do they represent some kind of crustal process that we don't know? We don't know that because we don't know where the meteorites came from. Context is everything. So getting samples from the moon is one thing. Getting samples from the moon that have some kind of recognizable context is the key goal. Next slide. Okay, humans and robots. I talked about this a little bit, but fundamentally, I think the paradigm that we're sort of proceeding is actually pretty good, and this follows largely, believe it or not, what was done on Apollo, and that is unmanned robotic spacecraft collect reconnaissance data that certify the safety or document what processes and what materials occur, followed up by humans who come and do the detailed work. So that basic template is actually pretty good. Get the reconnaissance data first, follow it up with people visits to do the detailed work later. However, maybe we can be a little bit better. Maybe when we go back to the moon, we can do things a little bit differently. what we can't, there's a lot of things we've talked about for the last 20 years as far as what we'd want to do if we went back to the moon. One of the things is this idea of a human-machine partnership. And what I have in mind when I talk about that is you want to let people do what they do best, which is creative kinds of exploration and intuitive thinking and adaptation of plans in real time. But yet machines can make that a lot easier. To give you one example, I landed an area. It's fairly complex, and I want to get the maximum diversity. But I don't know where I should spend most of my time. My time is very valuable, right? It may cost several tens of million dollars a minute for me to stand on the moon in my pressure suit and my geological hammer. If I had a rover that went out ahead of time, say a few days to a week before, and went around and sampled the various units that I think exist, now I have a data set, and I can prioritize the targets. Well, this one looks the most interesting, so I'm going to make a beeline there and work there and see what's really going on. Maybe that's the key to the whole thing, or maybe it isn't. Maybe then I can go to the next most important one, visit that, and see what's going on. In the old LIMPO days, back in the 90s, this was called pre-reconnaissance. The idea is you send a rover out to reconnoiter a site, followed up by detailed work by the people when they were able to come. I think that makes a lot of sense to me. Another example that you could do is you could land a robotic rover at a site, have it go around, collect a reference sample from all the units over a course of several weeks. Then when the people land on the moon, the first thing to do is they pick up that bucket, throw it onto the ascent vehicle. They've already got a top-level sample of the entire site. Then they can go around and follow up with detailed work on the sites that look most interesting. So using robots and people creatively together is something that hasn't really been tried in the space program because we haven't built the kinds of machines that lend themselves to that kind of cooperative, iterative work. The thing that I've been particularly interested in is the idea of robotic telepresence as a way to project a human mind into a machine. Now, I think this might actually be a very useful technique, especially useful for sites that for various reasons either are totally inaccessible or extremely difficult for people to work in, even with good environmental control systems. An example might be, for example, the permanent coal traps near the poles. Right? It may well be that we don't want to send people down in those for a variety of reasons, both to contaminate the environment and also perhaps for the reason that their suits aren't going to work very well down there. But sending rovers down might be the way to do that, and actually being able to control a teleoperated, telepresence kind of rover might give you the impression that you're actually in a remote alien environment. I think it has a lot of potential value. Whether it can actually work in real practice, we don't know. It's something we need to learn when we go back to the moon. Next slide. All right, you've seen these before. I just want to briefly cover it. This is the template of Apollo, where we had impactors, soft landers, and orbiters. And some of these orbiters, by the way, post-date Apollo. Basically, Clementine, Prospector, and Smart 1 were all recent missions. But they're sort of different levels of capability and information. With an impactor, you can collect data till it hits the moon. With a soft lander, you can collect data for a limited amount of time, depending on what kind of power source it has and what kind of capability it has. With orbiters, you can continually collect data for long periods of time, but it's all remote data. So each of these types of mission have their place. Next slide. We currently have 2 orbiters orbiting the moon. We're going to have 2 more in the very near future. In fact, I'm going to India next month for the launch of Chandrayaan-1. We're going to launch in October. And hopefully that'll be a successful mission because this is the first time we're actually going to fly an orbiting imaging radar to look into the dark areas of the poles on this mission. And finally, there's the Lunar Reconnaissance Orbiter, which will launch sometime next year. All of these are polar orbiting missions. They all will collect good regional global data. None of them have the ability to provide ground truth, with the possible exception of the L-Cross impactor on Lunar Prospector. By the way, there's an impactor on Chandrayaan-1 too. And instead of heading for a shadowed area, they're actually going to try to hit a lit area. They're going to plow this into Malapert Peak, which is the mountain sticking up in the sunlight near the South Pole. Next slide. Basically, from these missions, we will get the best possible data I could imagine. I mean, if I were sitting down in the early 90s and I had to list what would be my desired list of lunar remote sensing data, I couldn't come up with a better list than this. Because after these missions fly, we're effectively going to have the complete moon covered at very high resolution for topography, for mineralogy, and for geochemistry. So there's actually quite a bit of very high quality information and science that can be done with this. Next slide. Okay, so what do we need to do this? If we go, I've talked sort of about operational philosophy. What actual physical equipment do we need? Fundamentally, the Apollo tools and the Apollo field equipment were pretty good, and there's no reason to significantly change those, with a few exceptions. You might want to actually, as I mentioned before, do some sample analysis, not only in the habitat before you come back, but also in the field. And for example, they now have these things, portable X-ray spectrometers. You can hold the instrument against a rock and get effectively a chemical analysis in a few minutes. That would be very useful in sampling things like big melt sheet boulders where we might have subtle variations in composition along them. I don't think there's a need to do significant drilling. There's a lot of effort on Apollo doing regolith drills, and in some cases it took a lot of the astronauts' time to extract those drills, although that was a problem that was solved after Apollo 15. But effectively, I think that the moon provides a lot of natural drill holes for us. That's the craters. Effectively, craters of all the various sizes that occur on the moon dig down into the moon and excavate stuff from the subsurface. Sampling crater ejecta is one way to look at the subsurface on the moon without drilling. And if drilling is a mass and power-intensive and time-intensive activity, I would much rather spend the time going around doing a comprehensive sample of craters in the site to unravel the subsurface than I would in drilling the site. Effectively, we need to think more about how do we plan this and how do we use robots and people together, as I mentioned before. I think pre-reconnaissance is actually a very good strategy. I think that's a way to high-grade the science immediately so that you can focus human time on the most pressing problems. Another thing that we mentioned earlier is this regolith study. By that I mean we sort of understand in first order how the regolith forms. You have a rock exposed to space, it gets hit by cratering, it grinds up into a surface powder. But actually understanding how that process occurs in detail is still somewhat unknown. And one of the things that's been proposed for a long time, Dave McKay came up with this idea, is to actually make a big trench, where you, just like a trench on the Earth, where you expose the shallow subsurface in a wall and basically sample and study that wall in detail at very fine intervals. I think that would tell us a lot about both the flux, the impact flux of the moon, and also, remember, the regolith theoretically, at any point on the moon, you have a sample from anywhere else on the moon because the stuff is thrown ballistically. So in theory, you might have samples from very distant sites contained within this exposure that you would recognize and be able to sample. Next slide. Okay, sorties versus the outpost. I threw this in because I know that in the ESAS there's mention of sortie missions and there's mention of outpost. I think each of them offer opportunities, but they're slightly different. The sorties I look upon as sort of super Apollo missions, where the idea is you go to a site, you study the hell out of it for a week, and then you leave forever and you never come back. Now you might come back. You might do a sortie mission to a site that's so interesting you decide you want to put an outpost there. But fundamentally the premise behind the sorties is geological diversity. So you'll go to complex sites with a lot of multiple objectives, and fundamentally it's good for geoscience. But an outpost is, in contrast, when you go to one site, allows you to build up capability, because every time you go to a sortie site you throw away that much capability, and that's a fairly big financial hit. If you go to an outpost, you're able to build up capability with time. Also, for certain activities, like for instance resource utilization or facility installation, you want an outpost. You don't want to be able to you don't want to have to plan to put an observatory in place on a sortie mission. That's not what you do on a sortie mission. You basically use geoscience. The point of these is that they both offer different things, and what's good for some may not be good for another. My own personal preference on this, and since I've got the floor, I'll go ahead and give it, is that I much prefer the outpost. Now you might think that's kind of strange, because I'm a geologist and I would love to go and visit 53 sites on the moon. But fundamentally, I think by going to an outpost and building up capability there and building the ability to extract what we need from the local resources, that gives you global sortie access. Basically, I want all the sortie missions, but I want them staged from the moon, not from the Earth. And fundamentally what that involves is ISRU and reusable propulsion systems, fundamentally. And once you've got that, you got the whole planet. You don't have one site, you've got the entire planet. Next slide. Okay, let's talk a little bit about stations and observatories. We know this worked on Apollo. It was the thing, I think, if you asked all the moonwalkers what they liked least about their moonwalks, they'll all say is putting up the ALSEP. because fundamentally that was looked upon as overhead. It was kind of a pain. Sometimes things didn't go well. It was an enormous time sink. Usually one EVA was devoted to the ALSEP deployment. And so that was a significant time hit. And now the other side of that is those ALSEPs worked superbly, and they worked superbly for a very long period of time. But what do we learn from that? When we place stations and things on the moon, how do we want to do that? And these are some of the things I've thought of. Automate the deployment. How do you prepare the site? Do you want to use local resources in part to make surface systems and installations? How should these be powered? Fundamentally, the reason the ALSEP was so successful was it was RTG powered. So you didn't have to worry about sunlight. It worked all the time. Once it was turned on, it worked continuously until it was turned off. And then, do any of them require maintenance? Next slide. Okay, what are the kinds of stations we're talking about? I've just put up a list here of some of the sciences that have indicated an interest in setting up stations on the moon for different types of science. Fundamentally, geophysics involves studying the subsurface and the whole body of the moon. And that involves looking at the seismicity of the moon, measuring the heat flow of the moon, looking at magnetic fields. Astrophysics involves a wide variety of different kinds of observations. The thing they're focusing on most significantly now are radio observations in spectral bands that we can't see from the Earth because of the Earth's ionosphere. So, for example, there's a lot of interest in looking at the low-frequency sky in radio wavelengths from the far side of the moon, because there's no ionosphere on the moon, and also there's no interference from the Earth's radio noise on the far side. Heliophysics looks at the solar wind and the sun, and basically as the Earth moon moves in and out of the geotail, you can actually map that out in some great detail. Finally, there's a community that does want to look back at the Earth for a variety of reasons. There's a different class of measurements that you can do uniquely from the moon that you can't really do from the Lagrangian points or from GEO that you can do on the moon. Next slide. So, how do you find sites on the moon? Purely flat sites are very rare. We talked a little bit about the terrain in a couple of these talks. There are craters everywhere, and those craters in the tens to hundreds of meter size range are what's responsible for the meter to tens of meter length scale surface slopes. And those slopes can be quite steep. They can be up to 20, 25, 30 degrees. But typically, they're not that bad. You do find all the Apollo sites, even Apollo 16, which went into the highlands, and both John Young and Charlie Duke continually remarked on how rough the surface was when they expected planes and they had all this undulation. That was all due to overlapping craters. Yet, they were able to find a nice flat spot to deploy the ALSEP. And it's especially true at the sites like Apollo 15, where they had a very nice flat site. However, when you have bigger installations, the bigger installation you have, if there's a requirement for flatness, you're going to run into difficulty. And one example is very low frequency radio observatories, which basically require dipole antennas to be laid out on the surface and such that they can communicate with each other, because you want to operate them as one big array. And so fundamentally, finding very flat terrain to do that is going to be somewhat difficult. You might find isolated flat terrain elements that you can link together somehow in a data sense, but that's going to be a challenging thing to do. There are hazards. There are seismic hazards. Topographic, by that I mean if you don't necessarily want to put a station at the base of a hill where that's on an active fresh talus slope, because if there's a big impact and the moon shakes, you might get debris that comes down and buries it. I don't think that's very likely, but it's possible, because we have seen recent landslides on the moon. We can see them on the Apollo photographs. The thermal environment, actually, I think this is probably going to be the easiest thing to deal with, and that is the more you can bury your instruments, the better off you'll be. If you get down to a meter or below that, you're not really going to have the diurnal temperature variation that you see on the moon, from minus 150 to plus 100 centigrade. And I don't think the micrometeorite environment is an issue at all. There is an issue, a question about the secondary ejecta environment. That's not micrometeorites in space, but secondary ejecta formed when a meteorite hits the moon and kicks up local dust. There's a constant rain of that secondary ejecta. It's very, very slow. It's not really a hazard, but it may actually affect the performance of certain very delicate instruments over time. Next slide. So how do we do this? Well, actually, instrument deployment was not too bad in Apollo, but the astronauts, all of them said that they wish they had one thing where you could just push a button and the thing would deploy, and they could go away and not pay any attention to it anymore. I think a key thing that we need to to include in future experiment packages is they should be repairable. So in other words, you want to plan for automated deployment to the extent you can. But if things go wrong, the astronauts should be able to get into the nuts and bolts and be able to fix things. And of course, the classic example Dean talked about last time was the Apollo 16 heat flow experiment. The cable was pulled out at the base of the connector, could not be reattached. So you ought to at least carry spare parts or replaceable parts if you can. Power systems, I think, are the big long pole. Fundamentally, no one's come up with a better power system than an RTG, but RTGs are hard to come by. So I think one key thing to look at is the possibility of rechargeable fuel cells. If you have something that can basically operate as a fuel cell at night when you don't have sunlight, and then basically crack that water back into hydrogen and oxygen in the daytime when you have solar power, that might be a way to get this constant power as well. One of the things we're going to want to do is to network stations. And placing a station is one thing. Having a station work with another station is something else entirely. Now, typically, the Apollo stations were not networked physically except through Earth radio. So effectively, we were able to receive observations from multiple stations simultaneously. And an example of where that's important is in a seismic network. You want to know at each station what the arrival time of a seismic wave is, because that will help you pinpoint where it came from. And also the characteristics of that seismic wave will allow you to infer what the structure of the outer part of the moon is. So in that sense, multiple stations all transmitting at the same time are networked through the Earth. There may be stations where you want to network on the moon. For example, it's often been talked about is to put, if we have an outpost, for example, at the South Pole, which is here near the crater Shackleton, Malapert Mountain is up here, and that's about 150 kilometers away. Now, ordinarily on the moon, that would not be visible because the moon's curvature is much more abrupt than that. But this thing does stick up way high, as you can see in this Selene picture. Malapert Peak is sticking way up here, and it is visible from the rim of Shackleton. So the line of sight connection between an outpost here and an observatory or a power station on Malapert is another example of how we might want to link two sites together on the moon, both in terms of data and in terms of other things, like, for instance, power transmission. So in placing these and in placing a data system, a data comm system to support that is an important part of the infrastructure of a lunar outpost. Anything that's basically placed on the limbs of the moon, which is around the 90-degree longitude lines, or the far side, is going to need some kind of communications relay to be in contact with the Earth. And I don't think we're going to want to be out of contact with the Earth for very long periods of time. On the poles, you're out of contact with the Earth about 2 weeks out of every month. So the Earth rises above the horizon and sinks below the horizon as the moon bobbles back and forth. Next slide. All right, observatories. This has been talked about for a long time. The astronomers are not now terribly interested in optical astronomy from the moon's surface, largely because they're under some mistaken impressions about the environment of the moon's surface. But my prediction is that will change, and in 10 years they will be talking about optical arrays on the moon. And if they do that, how are you going to emplace those kinds of things? There's a lot of trade-offs. You may want to do, if you want to look at the whole sky, you need to put your telescope near the equator, because effectively that will allow you whole sky access. But if one hemisphere is adequate, putting them at a pole is perfectly adequate. Do you use ISRU materials in constructing them? Because if you do, you can build much larger, much more capable equipment than if you have to transport everything from the Earth. You can use natural terrain features, and not only terrain features, but environmental features. For example, if I could build a lunar Arecibo by lining a bowl-shaped crater with chicken wire. The same token, if I wanted an IR telescope, I could put it in the bottom of a polar crater and have it automatically cooled, a cool detector without cryogenics, which is a big advantage, big power advantage. Putting in features like that, I think, will basically require human intervention and human supervision at least. We want to be able to do as much of this with robotic telepresence or teleoperations as we can, but fundamentally some of these things are very delicate. They're going to need human intervention, as both the ALSEP and the Hubble Space Telescope experience has told us. Next slide. Okay, so these are some of my conclusions from this. I think you want to design these packages so that they require minimal human interaction, but can be fixed by humans if possible. Site preparation can be largely automated. I think you can have robots prepare sites fairly easily before people come. They don't need to waste time doing that. And power systems are the long pole that we don't know the answer to that yet. How do you network things? There's been a lot of talk about using wireless routers as networking tools on the moon. That actually will work pretty well for a small local area. Once you get past a certain radius, it's not going to work very well. But anything that you put on the moon as an installation, as a station, as an observatory, should be serviceable by people if you need to. Next slide. Okay, I just want to close with a couple of challenges. I talked about this before. This is the range of experience of working on the moon in surface lighting that we have from Apollo. The lowest sun angle was 7.5 degrees in Apollo 12, and the highest one was 46 degrees in Apollo 16. We do not have any experience working at 1 degree sun angle, which is the sun angle at the lit areas at the poles of the moon. Next slide. So how are you going to deal with that? I think fundamentally we need, this is an unknown, it's a challenge. I don't think it's an insolvable problem, but I think working in the polar areas, whether you're in the lit zone or whether you're in the dark zone, you're going to require artificial light. It's going to require that just for safety, if for no other reason. So that's an operational challenge. I don't think it's an insoluble one, but it is something that we don't really know how to do yet. Next slide. Dust. Dust is everywhere. It gets in everything. It's a disaster. It's the end of the world. Next slide. I don't believe that, okay? I think there's a lot of mythology about dust. Some of them I'm stunned are even coming up now. Pyrophoricity. That actually came up in Apollo. And the idea here was, the hypothesis was, the lunar soil was so reduced that when the astronauts got back into the LEM and they repressurized it with 100% pure oxygen, the LEM would burst into flames. I'm not making this up. That was actually advocated by a legitimate, serious scientist in those days. It has resurrected itself. It has come up again. Only in this case, there's a slight variation. We have very high hydrogen content soils in the poles. So when we pressurize the LSAM with oxygen after we come in for an EVA, that's going to explosively combine and make steam. So we'll get another explosion. And if you don't get exploded by that, there'll be electrostatic discharge, which will be like a giant lightning bolt in James Arness and The Thing. Or you're going to have floating dust that's going to get in everyone's eyes and working in moving parts. All these have been proposed as processes. There may be some grain of truth into this as a process. I don't think any of them are as bad or as hazardous as people have been led to believe. A key thing that you remember about the dust is we look at the fender from the LRV and we look at the picture of Gene Cernan I showed in the previous slide. How relevant is the Apollo experience to dust control? Because I think in part we're somewhat misled by that experience. The Apollo suit had very limited mobility. And what the astronauts found very early in the EVAs was rather than using tongs to pick up rocks, it was easier for them to fall on their face, grab a rock, and then do a one-handed push-up to get back on their feet. And they did that repeatedly. And that was great fun. Oh, this is the gas. I don't need the tongs. Who needs the tongs? This is fun. Well, the problem is every time you do that, you get a little dirtier. And then, oops, I missed that one. I fell on my face. Oh, that's good stuff. I can get up, and I do multiple steps getting up. And you see this on the videos if you watch any of them. In some cases, when they're working with ALSEPs and equipment, they actually got down on their knees and wallowed in the dust. So a lot of the dirt in the Apollo suits, I think, was actually deliberately implanted because the astronauts were having fun, and they didn't have to worry about the thing working for the next 2.5 months. They just went and they're having a good time, and it was easier for them to operate because of the restricted mobility of the Apollo suit. So I don't think Apollo is particularly a good teacher in terms of the dust. But a key thing to do to stop a lot of the dust hazard is to keep things as clean as you can. And there's a lot of different ways to do that. And they're being looked at actively. One of the coolest things, I think, to come out in the last few years is this stuff. A lot of it is magnetic. And this is something that, amazingly enough, wasn't really very well appreciated in the early days of the lunar sample analysis because these dust grains have this nanophase metallic iron on the uppermost surfaces. And this occurs because you vaporize iron oxides, all right? It gets reduced into native iron, and these things actually recondense on the surfaces of dust grains. So when you pull a magnet next to it, the stuff is attracted to it. There's actual experimental data that shows this, where they actually, Larry Taylor has a little glass vial of dust. He has a magnet, and it's just like iron filings. It's the stunning stuff. So that suggests to me that dust as a hazard in the cabin, in the suits, and moving parts actually is probably overrated. I think it's something that can be addressed fairly simply. Next slide. So what do we conclude? We don't know everything. One of the reasons we're going to the moon is to learn these things. Right? How do you explore a planet? How do you live on a planet? How do you do geology best to get the maximum return from the minimal investment of time and effort? Those are the things that we're going to learn on the moon. That's why we're going to the moon. And Apollo was a great experience. It gave us a great baseline. We now know for sure what doesn't work. We know what works well, and we know what works sort of. And this is going to build on that experience. I want to use robots and people appropriately, use robots for the appropriate tasks and people for the appropriate tasks, and learn how to deal with the environment and in placing equipment such that we maximize the return in terms of knowledge, minimize the hassle and the effort of the people. Next slide. I put together a bunch of references and these are not all inclusive, but these are the things that I found that were most accessible in terms of getting to it on the web, and you can look at those when you download the presentation. Next slide. There's one more talk in the series, and that's going to be in 2 weeks by Kevin Ryder on meteorites from the moon. And next slide, please. I'll just close with that. Thank you very much. Answer any questions you've got. Yes?
Well, I have two questions. One relates to the meteoritic environment, especially during when the Earth-Moon system comes through a
shower.
Like in the mid-90s, there's the Geminids, and in 2001, the Leonids. I mean, those were predictable, and you could take preventive measures or not be on the moon, whatever. Any sense as to if you're caught in one of those or whatever? Do we know more about the impact rates and the velocities of it now versus Apollo?
Yeah, I think we do. I don't think we know enough, but certainly by the time we're staying on the moon, we'll have a pretty good feel about when to stay in the habitat and when not, and when to go out. Yeah, that's an avoidable phenomenon. That's the advantage of that particular phenomena is that occurs on a predictable, regular basis. Solar particle events don't, but at the same time, we're going to need some kind of a system to give us an advance warning of an SPE, so we'll be able to take cover from that too. And there are ways to do that.
My other question is, it was one of your previous slides. I'm not intelligent enough to know more about it. But at or near the lunar terminator, is dust elevated as?
Nobody knows.
Okay.
Well, I mean that's the answer. It's postulated that happens. And the idea is that there's a charge differential between the lit and the dark moon, and therefore this dust stuff is going to levitate. And there's an observation from Surveyor for sort of meter scale levitation, and then there's the observations from lunar orbit, which suggest hundreds of kilometers levitation. And both of those are controversial, and we don't know exactly how or if they're even real.
Can LRO try to repeat those observations?
They can try. We'd actually looked for that in Clementine. There were a bunch of images taken with the Star Tracker camera just before a lunar sunrise looking for dust levitation. Herb Zook actually requested these, and we took a whole bunch of data, and we never saw any evidence for it.
The LR cubes haven't gotten lower albedos, have they?
That's interesting because it depends on who you ask. When you send the laser pulse to the moon, you get it back from one of the LR cubes. You're only getting a few photons, so it's a very high loss path anyway. They never got very strong returns. They're still getting returns, and whether they've degraded over 40 years is a matter of debate. My sense is that they haven't degraded very much. Yeah, I made that argument that that's evidence that there's no large-scale dust levitation, but there are some people who claim otherwise. Again, it's like a lot of these things with the dust. There's how shall I put this best? Some people study stuff at the margins of knowledge and become convinced that it's extremely important, and it becomes a self-fulfilling thing that yes, it is extremely important because it must be extremely important because I'm interested in it. And why would I spend all this time studying it if it wasn't extremely important? But I would put the onus on the people that are saying these are hazards or issues for return to the moon. It's up to them to show that, and they have not done that yet. And they're very good at raising alarms, but they're not very good at documenting why this is a real issue. Now having said that, If they have specific measurements they want to make and as part of a robotic program to put this to rest or to verify that they're right and we're wrong, bring it on. I certainly don't want, I want to know. But my sense is that there is no real issue with that. I'll be hearing from them. Yes?
There's been some talk I've heard about putting the lunar outpost underneath a couple of meters of the regolith due to radiation concerns. What are your thoughts on that because of the difficulties of doing that versus the benefits?
There are a lot of good reasons for having habitats underground. That's why a lot of talk in the 80s and 90s was looking for lava tubes on the moon. If you had a lava tube, you can stuff a habitat in it, and you're protected from radiation. You've got a nice benign thermal environment, and it's just wonderfulness. The problem is, well, we don't know if there are any void tubes on the moon. We know there are lava tubes, or there were lava tubes. We don't know if any of them are void. You know, a lot of lava tubes on the Earth, when the lava stops flowing, the lava just sits there and chokes it and fills it. Right? Very few tubes where the lava drains out and leaves a void, and that's why there's such tourist attractions when you have them. You know, people come to see them because they're really cool. Now you could have that on the moon, but we don't know that they exist. The problem with burying habitats is twofold. It's a huge energy sink, however you want to do it. All right? One possibility, the best way might be to put an explosive charge, drill a hole, put the explosive charge down, and set it off, and make a crater, and then set your habitat in that, and then doze the soil up over it. That might be a good way to do it. But if you actually dig a trench and bury a habitat, that's a huge, difficult problem because the stuff on the moon is not easy to dig through. It compacts, it self-compacts as you go down. The other problem is, even if you are buried and you are able to do thermal control, because you're going to have radiators to get rid of the waste heat and do all that stuff anyway, you still have a problem with the interaction of that stuff that's on top of your habitat with the cosmic rays. And in fact, sometimes you get cascading secondary reactions from cosmic ray interaction that are worse than the cosmic radiation that you're protecting yourself from. The ideal way to protect yourself from radiation on the moon, I think, is to jacket everything with water. Because water is the best radiation shield. It's used in reactors on the Earth. And if you're manufacturing water as part of an ISRU thing, it's a good place to store it. You just have basically a big bladder that covers your habitat, and you can store the water in that. That's my preferred solution. Now, and also the people that worry about this stuff tell me that there are lightweight plastics that are very good radiation shields as well. Anything that has a lot of hydrogen in it, bound hydrogen or water, is a good radiation shield. Yes, Dean.
Relative to the burying, think about taking a Winnebago to the beach in Galveston and burying it under 2 meters of regolith. Think how hard that would be, and that's what you're talking about. It's not a trivial thing.
Yeah, it's very difficult. It's a lot of work. I thank everyone for coming. It's been a lot of fun, and hope you've gotten something out of this series. Appreciate it.